So we are talking about equilibrium and how equilibrium is affected by changing temperature. And the way that we do that is with something called the Van Hoff equation. So the Van Hoff equation is allowing us to determine how changing temperature impacts equilibrium constants. So this formula is going to look very similar to formulas that we've used in the past for vapor pressure and temperature, the Clausius-Clapeyron equation. Here it is. So it says the natural log of K2 over K1, and these K's are the equilibrium constants, equals delta H, which is the enthalpy change, over R, which is 8.314 joules per mole Kelvin, times 1 over T1 minus 1 over T2. So again, these K's, these are the KC's or KP or whatever you're talking about. They're the equilibrium constants. Delta H, this is the enthalpy change. It's usually in kilojoules per mole. Delta R, sorry, not delta R, just R. This is 8.314 joules per mole Kelvin. Something to pay attention to is that delta H is usually going to be given to you in joules, and delta H is in kilojoules and R is in joules. So I will usually just say 8.314 times 10 to the negative third kilojoules per mole Kelvin, so that then your units are the same. You either have to change delta H to joules per mole or change R to kilojoules per mole. And then because this unit here has a unit of Kelvin in it, you just need to make sure that your temperatures are in Kelvin. So let's look at an example of this. So this is not a new formula. We're just using it in a different way. It's called the Van Hoff equation. It's the same thing that we did with vapor pressure. It's the same thing that we did with kinetics, looking at rate constants. Now we're just applying it to equilibrium constants. Okay, so here is the problem. Let's look at the problem before that we were just doing. And let's say if the Kc of a reaction is 115 at 25 degrees Celsius, what is the Kc at 100 degrees Celsius? So this is the problem that we just did here with the hydrogen and the fluorine giving us hydrogen fluoride. The Kc was 115 at 25 degrees Celsius. So now we're just going to see what is the Kc if we increase the temperature to 100 degrees Celsius. So I'm just going to write down what we have. So this is the K1 is 115. K2 is what I'm solving for. What is the Kc at 100 degrees? That makes T1 25 degrees Celsius, which we're going to add 273 to get 298 Kelvin, because that's what needs to go here. T2 is going to be 100 degrees Celsius plus 273 is going to be 373 Kelvin. So now we're just going to plug this in and solve for K2 in this case. Oh, I also need to tell you that the delta H of this reaction is negative 180. We'll say 1.8 times 10 to the second kilojoules per mole. That would also, you would need that information. Okay, so let's plug it in. So we'll say the natural log of K2, which I don't know, over K1, which is 115, no unit, equals delta H, which we said is negative 1.8 times 10 to the second kilojoules per mole, over R, which we know, I'm going to use this one because I have kilojoules, 8.314 times 10 to the negative third kilojoules per mole Kelvin, times 1 over T1, which is 298, minus 1 over T2, which is 373. And now I'm going to solve. So I'm going to solve for this side first, and then I'll show you how to get rid of that natural log. So I'm going to say 1 divided by 298 minus 1 divided by 373 times, and I'll just do this separately, negative 1.8 times 10 to the second divided by 8.314 times 10 to the negative third. So that number times this term, 6.747 times 10 to the negative fourth. This should give me negative 14.61 something. So I'm just going to say on this side, negative 14.61. That's what this whole piece is. So then I have the natural log of K2 over 115. I need to get rid of this natural log term. The way I do that is to just exponentiate both sides. You raise both sides to the e. So if you look at the calculator right here where the natural log is, if you do the second, above it, it is the exponent key, the e key. So I'm going to say e to the negative 14.61 equals 4.52 times 10 to the negative seventh equals K2 over 115. I'll multiply both sides by 115. And get K2 equals, with, we'll say, 2 significant figures, or maybe we'll say 3 significant figures. We'll change this, put a little decimal place there. 5.20 times 10 to the negative fifth. So this is the K2 if we increase the temperature. So let's think about what this means in terms of Le Chatelier's principle. So you can always think about if this makes sense to make sure that you didn't make a math error somewhere. So let's see, does this make sense? Okay, so what happened is we increased the temperature from 25 to 100, and the equilibrium expression went from 115 to 5.2 times 10 to the negative 5. We also have this information here, delta H is negative, which tells me that this is an exothermic reaction. Remember what we know about exothermic reactions. Exothermic reactions means heat is a product. In this process, we are increasing the temperature. Increasing the temperature is the same thing as saying increasing the concentration of a product. Increasing the concentration of the product means it would shift the equilibrium to the reactants, which is exactly what has happened. We went from a Kc that favored the products, to now a Kc that's less than 1 that is going to favor the reactants. So this is something that you should be doing through all of these problems to think about, does your answer make sense? You know what the Kc is supposed to tell you. So does that logically agree with what your math tells you? A lot of times it's easy to miss a sign in your calculator or forget an exponent, and thinking about what logically makes sense will help you make sure that your math agrees with the chemistry.